Welcome to this explainer. Look, if your organic chemistry and all those naming rules have ever felt like a giant puzzle to you, you're in the right place. Today we're tackling halogen derivatives. We're going to decode the patterns, skip the memorization, and really figure out the logic behind these awesome molecules together. So let's just jump right in. So, what exactly happens when you swap out a hydrogen for a halogen? You know your basic hydrocarbons, right? Like methane, just carbon and hydrogen chilling together. But imagine taking one of those hydrogens and kicking it out, replacing it with a halogen like fluorine, chlorine, bromine, or iodine. The second we make that swap, boom, we completely transform that basic hydrocarbon into an entirely new compound with its own wild, unique properties. It's a real game changer. To get there, here's our roadmap for today. First, we'll meet the halogen derivatives. Then, we'll hit classification and cheat codes, see how to actually make them, look at their physical properties and behavior, and finally, we'll explain optical isomerism.
All right, Section 1. Let's officially meet the halogen derivatives.
Whenever you spot the general formula R-X, you're looking right at a halogen derivative. It's that simple. The R is just your carbon framework, your alkyl or aro group, and that X, that is your halogen. So if we take methane and swap one hydrogen for a chlorine, we get chloromethane. It seems like a tiny substitution, but honestly, it changes absolutely everything about how that molecule behaves.
Moving right along to Section 2, classification and cheat codes.
Now, when you've got two halogens attached, which we call dihalogen compounds, you're going to see two terms pop up all the time, vicinal and geminal. Here is a massive cheat code to remember them. V for vicinal literally means very close or neighboring. So if the halogens are on side-by-side carbons, it's vicinal. Geminal, on the other hand, means they share the exact same carbon. Just look for that spatial difference and you'll nail it every time.
We can actually break these down into 6 different structural groups based entirely on where the halogen is sitting. If your halogen is hanging out on a standard sp3 carbon, meaning a carbon with only single bonds, that's an alkyl halide. What if it's on an sp3 carbon right next to a double bond? That's allylic. Next to a benzene ring? Benzylic. Now what if it's directly in the action? Directly attached to a carbon-carbon double bond makes it vinylic. Directly on a triple bond is a haloalkyne. And if it's stuck right onto an aromatic benzene ring, we call that an aryl halide.
Okay, pay close attention here, because people mix these two up all the time. You have to check exactly where that halogen is relative to the ring. Take benzyl chloride. The chlorine is attached to a carbon atom that's just sitting next to the benzene ring. That makes it benzylic. But look at chlorobenzene. There, the chlorine is slapped directly onto the benzene ring itself, making it an aryl halide. Spotting that direct versus indirect attachment is absolutely crucial for understanding how they're going to react later.
Let's look at another super handy trick for figuring out primary, secondary, and tertiary alkyl halides. The golden rule: do not count hydrogens. Seriously, that's where everybody trips up. Instead, focus only on the carbon holding your halogen and ask yourself, how many other carbons are directly attached to this guy? One carbon neighbor? It's primary, or 1 degree. 2 neighbors? Secondary. 3 neighbors? You guessed it, tertiary. It really is just that simple.
Okay, Section 3. How to make them. Let's get into the chemistry of actually building these things.
The go-to way to make alkyl halides is actually starting with alcohols, trying to swap out that OH group for a halogen. You've got a few options. You could use the Lucas reagent, which is HCl with zinc chloride. You could throw in some PCl5, but the absolute best method, and trust me, board exams love to ask this, is using thionyl chloride, or SOCl2. Why? Because when it reacts with an alcohol, the byproducts are sulfur dioxide and hydrogen chloride. And here's the kicker. They're both gases. They just bubble right out of the flask, escaping into the air, and leave you with a perfectly pure alkyl chloride.
Now, trying to add iodine or fluorine directly is a nightmare. Fluorination is way too violent, and iodination goes backward just as fast as it goes forward, so we have to be clever. Enter 2 famous named reactions, Finkelstein and Schwarz. I want you to memorize this. Finkelstein goes with iodine. You use sodium iodide and acetone to swap out a chlorine or bromine for an iodine. Schwarz, on the other hand, goes with fluorine. You use a metallic fluoride, like silver fluoride, to pop a fluorine atom right into place.
When we want to make aryl halides, where that halogen is directly on the benzene ring, alcohols aren't going to cut it. We need heavier artillery. We mainly use 2 methods. The first is electrophilic substitution, where you react benzene with chlorine and use a catalyst like FeCl3 to force the reaction.
The second is a huge one, Sandmeyer's reaction. Here, you take a diazonium salt, a really specific nitrogen compound, and treat it with CuCl for a chlorine or CuBr for a bromine.
All right, let's move on to Section 4, Physical Properties and Behavior. When we look at the trends as we go down the periodic table from fluorine to iodine, the patterns are fascinating. Halogens are more electronegative than carbon, so the carbon-halogen bond is always polar. But as that halogen gets bigger and heavier down the group, the bond itself stretches out, it gets longer. And because the atomic orbitals aren't overlapping as nicely, that really long carbon-iodine bond ends up being the weakest of the bunch. At the same time, boiling points generally shoot up as the halogen gets heavier. But a quick heads up, if your carbon chain gets super branched, the boiling point actually drops because the molecule gets more compact, which means weaker van der Waals forces.
Now, this leads us to a fantastic conceptual question, the kind that shows up on exams all the time. We just said the carbon-halogen bond is polar, right? And usually, polar stuff loves to dissolve in water, because water is polar too. But alkyl halides? They are practically insoluble in water. Why is that? Well, even though they're polar, they just can't form strong enough hydrogen bonds with the water molecules. The water molecules are essentially ignoring them, choosing to stick tightly to each other instead. Here is a perfect example of how a molecule's physical shape completely changes its properties. Take p-dichlorobenzene. The two chlorines are on exact opposite sides of the benzene ring, making it perfectly symmetrical. And because it's so beautifully symmetrical, millions of these molecules can pack together super tightly in a solid crystal. Better packing means a much stronger crystal lattice, which means you have to pump in way more heat energy to melt it. So it has a noticeably higher melting point than its lopsided isomers.
Okay, final stretch. Section 5, Optical Isomerism Explained.
Do me a favor and look at your left and right hands. They look totally identical, don't they? They're perfect mirror images. But try to lay your left hand flat right on top of your right hand, palms facing the same way. You can't do it. The thumbs stick out on opposite sides. They are non-superimposable. Well, guess what? Certain molecules do the exact same thing. In chemistry, this wild property of having a non-superimposable mirror image is called chirality. So how do you actually spot chirality in a molecule? You hunt for a chiral center. A chiral carbon is just a single carbon atom attached to 4 completely different groups. If you see a carbon bonded to, say, a hydrogen, a chlorine, a methyl group, and an ethyl group, like we see in 2-chlorobutane, you've got one. Finding that carbon with 4 unique partners guarantees the molecule will have a mirror image that just won't overlap. And the coolest part is how we actually measure this in a lab. If you shined plain polarized light through these compounds, the 2 mirror image molecules interact with the light differently. One version of the molecule, one enantiomer, will twist that light to the right. We call that dextrorotatory, marked with a plus sign. Its exact mirror image will twist the light to the left. That's levorotatory, marked with a minus sign. It's an invisible 3D structural trait revealing itself right before our eyes. Now think about this. What if you have a beaker filled with exactly a 50-50 mix of both enantiomers, half plus, half minus? We call that a racemic mixture. Because half the molecules are twisting the light, say 20 degrees to the right, and the other half are twisting it 20 degrees back to the left, the effects completely cancel out. The net rotation is just 0. Thanks to this external compensation, a racemic mixture is completely optically inactive. All right, let's lock all this down before your next exam. Here is your ultimate memory cheat sheet. R-X is your halogen derivative. Vicinal means neighboring halogens. Geminal means same carbon. For your degrees, just count the carbon neighbors directly attached to the halogen's carbon. SOCl2 is the ultimate way to prep them. Finkelstein equals iodine, Schwarz equals fluorine. And if you spot a carbon hanging onto 4 different groups, you've found a chiral center. I want to leave you with this thought today. We just saw that simply mirroring a molecule, changing literally nothing but its 3D spatial orientation, can completely reverse how it interacts with light. If a subtle, invisible shift like that can change a physical property so drastically, what other hidden patterns are waiting to be decoded in the 3D world of organic chemistry? Keep looking for those patterns and never stop questioning how the microscopic world shapes absolutely everything around us. Thanks for joining me for this explainer. I'll catch you next time.